Okay, today I'd like to share with you one problem, actually one example of separate differential equations. And the problem is right here. Okay, as you can see, I underline all the keywords. And also I draw a picture. Not really draw, but it's doodle. And the picture is not so nice, but you can imagine that on a sunny day we have one object which is moving with a constant velocity, and next suddenly we will have the wind. Okay, can you see the wind? Okay, and the wind will pull the object back. It will make the particle slow down. And the external resistive force is proportional to its velocity. So I write Ft, the force at time t is some constant, let's say k, times Vt. This one is magnitude. And we have to predict the velocity Vt at any positive time t. Okay? In other words, we have to predict the unknown function Vt. Now, let's use, I think we've already known from M1 that according to the Newton's second law of motion, we have, so Newton second law of motion, we have F, the net force, is the mass times the acceleration. Moreover, we also have that I here, the acceleration is actually the derivative of velocity. So A actually is the derivative of Vt. Okay. Now come back here. Let's choose the reference frame. The initial time is t0 equal to 0. It's when we start seeing the change in the velocity. Okay, and I draw the axis here along the line of motion, and the positive direction is the same as V0's. Okay, so the net force here, actually this one is minus k times Vt. And by minus side, I mean the force, the external force, opposes the motion. Okay, so we will have minus k times Vt equals m times V prime t. And this one, we got the differential equation that describes the dynamics of the particle. And as you can see here, this one is separable. It's separable. Okay? And now I'm going to solve it. Notice that at first the object is moving with a constant velocity, and by choosing a proper positive direction of motion, I have V0 is positive, and therefore before the object stops, the velocity here is positive. So let's divide both sides by Vt, which is positive. So let's say it's 1. So from 1 we have V prime t divided by Vt is equal to minus k divided by m. Now let's integrate both sides and we get like this. Pay attention, we don't have the absolute value, we don't have to write the absolute value of Vt because this one is positive. And in the right side we have this one times t, and of course two integrals will differ from each other by some arbitrary constant. So let's plus an arbitrary constant. Now we can get Vt is the exponent of c is power to the power of c multiply this quantity. Now pay attention, the initial condition here we have at the initial time the velocity actually is this one is v0. So at t equal to 0 we have v0 actually is v0, v at 0 is v0, and therefore as you plug in this equation you have v0, which is v0 is this one becomes e to the power of 0, and which is 1. So we have v0 is c, e to the power of c, the exponent of c. And finally we get our solution, which is v at time t is the initial velocity times e to the power, no, so I should say the exponent to the power of k minus k over m times t. So here we have the solution, and with this one you can predict at any time t the velocity. You know, you just plug in the t and you get the velocity, and also you can see that the velocity decays exponentially. Okay, so I'm done. Thanks for watching my video.